I wasn't sure what to make out of this news article when I first saw it. I like eating hash with bacon and eggs in the morning like everybody else. It wasn't clear to me why hash oil should have anything to do with it. And it wasn't until I started reading it that I realized they were talking about hashish. And that's kind of interesting. Whatever's going on here that looks like oil, maybe there's something related to hashish. So it looks from this article that there are problems with people starting fires when they're trying to extract compounds out of hashish, which is a form of marijuana. And so the idea is they've developed some process, and probably the problem is, you know that natural gas smells bad, and we talked about this. The reason that natural gas, which is very flammable and a real fire hazard, smells so bad is they purposely contaminate the natural gas in the lines that you have that supply your home. But of course, if you go buy a bottle of butane at the store, it doesn't have any contaminant in there to tell you when you fill the room with a highly flammable compound. So I got interested in this. I got onto YouTube, looked at a couple videos. It's kind of fascinating what creative people have done. So here's the idea, is that marijuana and hashish contain this compound, delta-9 tetrahydrocannaboil, binds the cannabinoid receptors in the brain and does all kinds of stuff. And I guess most people don't have access to the kinds of organic solvents that I have or every organic chemist has in their laboratory. So what do? They go buy a can of butane, which kind of looks like hexanes, which is an organic solvent. The advantage of this is it's very easy to evaporate. So we have very special evaporators in our laboratory that allow us to evaporate organic solvents. Here you don't need anything special. So it seems to me that what they're doing, you go to your local supplier, you buy a bunch of marijuana or some hashish, and you need some sort of a tube made out of metal that has a big opening here and a small opening at one end. And then you use a rubber band or something to tighten some cloth at this end so all the marijuana doesn't fall out when you invert it. And then you stick this can of butane right here on the end and invert it. And when you do that and open the valve, suddenly all this butane starts to spew into here. And of course, as gases and other things start to expand, they get cold, so even more of the butane expands. And so the butane goes through this tube and extracts out all the organic compounds, and it leaves behind the water-soluble compounds that aren't going to get you high, because all you care about is the greasy compounds. Now, there are lots of naturally occurring compounds in marijuana. All of them come out. But if you'd really like that concentrated THC. And then at the bottom of this, when you've turned it upside down, right at the bottom of this, as all the butane is dripping out the bottom, you catch it in a glass dish that's sitting in some warm water. And the warm water evaporates all the butane. And so what you're left with, as all the butane evaporates, is this waxy, honey-like substance that is super duper duper concentrated in THC. So I hope you use organic chemistry for more useful things than this, like curing cancer or diseases, but I thought that's a pretty clever use of organic extractions. And of course, if you're an idiot and if you're doing this indoors and your entire room is filled with butane vapors, the slightest spark is going to set that off, and the whole room will detonate in flames. All right, so let's get back to NMR. I'll bet THC has a cool NMR. I didn't bring that with me, but... So we have been talking about NMR on our last lecture, and we decided we were going to focus on carbon NMR because it's so simple. And because it is simple relative to proton NMR, that makes it very useful to you in solving problems, in solving spectroscopy problems. So my recommendation to you is if you're given infrared or proton NMR and C13 NMR data, go to the C13 NMR data first. It's easiest to get powerful information out of that. And I regret that in my last lecture I didn't quite have time to get to these chemical shift ranges for carbon NMR. All I really talked about was chemical equivalence and how many peaks you should expect in a C13 spectrum. So here's the general range for carbon NMR. Remember we said we weren't going to plot in terms of frequency, we're going to plot in terms of parts per million, which sort of normalizes for different magnet strengths. And the advantage of carbon NMR is that there's there's some very distinctive ranges for the chemical shifts of common functional groups. So if you have an aldehyde or a ketone in your molecule, and I'll try to abbreviate that like this, and I'll put H or R here, right? If you have an aldehyde or a ketone, it's going to show above 190 parts per million. That's the only stuff that shows above 190 parts per million. You do not need IR to tell whether you have a carbonyl in your compound. You can just look at the C13 NMR and know whether you have a carbonyl in your compound. And moreover, you can tell what type of carbonyl you have in your compound pretty reliably with C13 NMR. Okay, so below that we have a different type of carbonyl in this region from 155 to about 185. This is where we have carbonyl groups that have heteroatoms attached. And so what kinds of heteroatoms? For example, oxygens or carboxylic acids, acid chlorides, we'll talk more about those later in this quarter. Amides, where you have nitrogen attached to the carbonyl. So all of these different types of carboxylic acid derivatives where the carbonyl has a heteroatom attached, not carbon or hydrogen, will be in that range. Now, down here at 160 to 110, this is all the CC double bonded carbons. These are now carbons with no oxygen attached. It's just carbons that are part of a pi system. And it doesn't matter whether it's a benzene ring or a simple double bond, they show in that region. So you could just look in that region. If you see peaks in this region, yeah, you've got a CC double bond. And so I'll try above here to draw a benzene ring, because it doesn't matter whether it's a benzene ring or just a regular CC double bond during that region. Now there's one tiny little sticker here as far as chemical shifts, and that is if you have an alkene that is attached to a carbonyl like this carbon, the beta carbon, I'm going to circle it here in glorious pink, that carbon will sometimes appear down in this range. And it will look like even though it's not a carbonyl carbon, it will sometimes appear in that ester, amide, carbonyl range. And that's the only sort of tough part about overlap. There is a sort of overlapping area. I hate it when I see peaks at around 159. It's like when I see peaks at 159, see, that's that overlapping region. Then you're sort of left with a little bit of uncertainty. Gee, is that a benzene ring or an alkene, or is that a what is that? So, yeah, so let me just come back to this beta carbon thing. It doesn't always appear in this region. But it can appear in this ester amide region. So let me just point out that it could appear in either of those regions. Okay, what about things attached to single bonds? Everything else that has just single bonds attached to the carbon, that's all below 110. You don't get a whole lot of information. You can't count how many chlorines or electronegative atoms are attached. It's not as simple as that. Alkynes also appear at the upper end of this region, but you won't do yourself any good trying to figure out whether you've got alkynes or alkane carbons. You just count up how many carbons you have below 110. And that's all the stuff that's singly bonded, and triple bonds aren't that common, but or triply bonded. So those are the C13 shift ranges. If I give you a C13 NMR, not only can you count the peaks and have a good estimate for how many unique carbons you have in your sample, but you can also look at where those resonances occur, what ppm those resonances occur at, and get some information about, gee, do I have a double bond in my compound? Or is it probably a benzene ring? Or do I have an ester? Very powerful stuff. Okay, now you also have additional peaks in your spectrum, almost always. So in your C13 NMR, in this very tiny, maybe I can expand this using this fancy. So you will also have these other resonances in your NMR. So here's a picture of a section of a C13 NMR. And notice here it's 77 parts per million. There's 3 peaks. And you will see that in just about every single spectrum. It turns out that that's the carbon from deuterochloroform. Remember that solvent that I showed you in the last lecture? It just so happens that it appears as 3 equally sized peaks, and it is always at 77 parts per million. You have to dissolve your organic sample in something, right? And organic solvents will always have carbon atoms, so they'll always show up So don't treat that as part of your sample. This little peak here from the spectrum I took this from at 75.5, that is part of the sample, but those 3 peaks, it's part of the solvent. Ignore it. Don't get caught into trying to assign that as part of your sample. Now, we haven't done proton NMR yet, but when we do proton NMR, you'll see a similar contaminant type of peak. And this is chloroform. When you buy a bottle of deuterochloroform, it's not 100% deuterochloroform. It's 99.9% deuterochloroform. And the other 0.1% that you're buying in that brown bottle is just regular chloroform that has a proton on it. And that always shows up here at about 7.26 parts per million. So you should look for that peak at about 7.26 and don't treat it as part of your sample. That's the contaminant from the solvent, and it's there in most of the NMRs, because most of the NMRs I'll show you are carried out in deuterochloroform. Okay, so in C13, look for those 3 peaks at 77 and ignore them. And in proton NMR, look at a peak at 7.26. If you see it, ignore it. Okay, those are just from the solvent. Okay, so we're experts now on this chemical shift range business. And so let's see if we can apply this to a sample. Like a kind of typical problem that you might have to work. If you were in the lab, this is the way things work. So I've redrawn those chemical shift ranges up above. You just wrote that stuff down, so I'm just putting it here for your convenience. And so let's suppose you go into the lab and you think, well, I'm going to make an ether out of this alcohol, and I'll treat it with acids so I can make a leaving group out of the OH, and then I'll put some methanol in there. And then you isolate your product, and you're not quite sure what you got. So you go take a carbon NMR. And it's like, what is this thing I isolated? Well, I've got a carbon NMR, maybe I can figure that out. Well, it could have done an SN1 reaction like I was hoping for, but it also could do an E1 reaction. And there's 2 different types of E1 products you can generate, and how can you be sure which one you got, right? You know, these conditions may make that somewhat ambiguous. So this is where you get a chance to use spectroscopy to figure this out. And here's the C13 NMR below. And I can tell it's C13 just by looking at the fact that this goes from 0 to 200 parts per million. Proton NMR only goes to about 10 parts per million. As soon as I see this axis going to 200 parts per million, I know it's a C13 NMR spectrum. Okay, so the first thing I do is I look at this first. What you use spectroscopy for is you use it to rule out possible structures. So the first thing I do is I look at this product, this ether here, and I see, well, there's no double bonds in there, but look down here between 120 and 140 parts per million, right? There is no way that that's that ether, because this ether has no CC double bonds in it. There we go. It's gone, right? I know there's a CC double bond in this compound. So now the question is, okay, it looks like it was some sort of elimination reaction. Which of these 2 elimination reactions do I see? So I see some CC double bonded stuff, some singly bonded stuff in my carbon NMR. And so which one of these is... So probably the first thing that I would do is I would look and try to predict how many carbon signals would I expect in the C13 NMR. So I see 2 alkene peaks here, and those 2 carbons are different. One carbon has a methyl, one carbon doesn't. So I expect 1 peak and 2 peaks, and I see that. How many singly bonded carbons do I have? Here's a methyl that has only single bonds. Here's a carbon on the other side of that alkene that has only single bonds. Let me just start numbering. And this one is distinctive, number 5, number 6, number 7. So I expect to see 1, 2, 3, 4, 5 peaks in the singly bonded region. Well, that seems to match. There's 5 peaks here in this singly bonded region. I'm not going to cross that out. Everything I see in the spectrum is consistent with this compound. Let's compare this third compound here. So here I see 2 completely different types of alkene carbons. There's one with 2 H's on it, one with 2 carbons. So those are distinctive, 1 and 2. That would also match. Now I count over here at how many carbons I would expect to see that are singly bonded. And this carbon over here, number 3, is not distinguishable, is indistinguishable from that bottom carbon. Both of those carbons are attached to an alkene. They're both part of a ring. So by symmetry, I don't expect to see different signals for that. I only expect to see 1 signal for carbons 3 and 3, and 1 signal for carbons 4 and 4, and then that carbon at the far end will be a 5th signal. So in this singly bonded region, if this were the compound, I would expect to see 1, 2, 3 extra peaks, and I see way more than that. We're done with the problem. Immediately, As soon as I see that symmetry in there, I know that there's too many peaks here in this part of the C13 to be consistent with that. So that's a typical approach to carbon NMR. Counting the peaks is actually a pretty powerful way. Maybe I could have started with counting the peaks and probably answered this. I probably didn't need to look at that alkene region. But this is how you can use those distinctive peaks, like in the carbonyl region or in the alkene region, to give you a leg up on figuring out what your structures are. Okay, so that's the end of carbon NMR. So you're now ready to take this little chemical shift range chart and work bunches of problems to figure out, to help you rule out plausible structures. So now we're going to switch to proton NMR. And it's aggravating, it's more complex, and yet it is massively more powerful. I love the fact that it's way more powerful, and you think it sucks that it's way more complex, and whatever, that's just the way it works. If you spend a significant amount of time investing in learning how to interpret proton NMR spectrum, it's way more powerful than C13. Okay, so the first and most important thing you can do with a proton NMR spectrum, just like carbon NMR, is try to predict how many sets of peaks you should see, how many sets of types of unique protons you should see. And this is the same thing that I brought out with the carbon-13 NMR. So when I look at these molecules here, let me just redraw my bromopropane here. I don't expect these two protons on bromopropane to be different. They're both attached to a carbon that has a bromine on them. They're both attached to another CH2 group. Those two protons should end up giving one signal. And so I'll go ahead and label that as A. These protons over here are two carbons away from the bromine atom. They're attached to a methyl group. Those I would expect to give their own type of signal. And then finally we come out to the end one here, C, and all three of those protons in the end, I could say the same thing about their distances from the bromine and what they're attached to. So I would expect to see three sets of signals, or there's three types of unique protons in this bromopropane molecule. And so as long as I know that, I can very quickly rule out a zillion different types of compounds that would not fit with that spectrum. Okay, so let's talk about this other compound here. I see two protons attached to this alkene carbon at the top, and those are indistinguishable. Each proton is cis to a methyl and trans to a methyl. I could say the same thing for the other one. So I would not expect these two protons to show up any different. And so I'll label them. You can label them 1 and 2. I don't know why I chose to label with A and with letters here. And now that the protons on this methyl group over here on the right-hand side is no different from the methyl group on the left-hand side, I would expect those to be non-distinguishable. So really I would expect to see two types of protons in my proton NMR spectrum. And just from knowing that, I could rule out a whole slew of different spectra. Okay, so here's another compound that is an alkene, and the difference now is that each side of this alkene is differentiated. On the right-hand side, I have a chlorine atom, and on the left-hand side, I have a methyl. So now when I look at the two protons on the top, I can see one of those protons is cis to chlorine, and the other isn't. Those are different. Being cis to chlorine is not the same as being trans to chlorine. And so I would expect these two protons to be different. And you can't rotate about that CC double bond. The CC double bond locks those, the geometry of that carbon atom. So I would expect to see three sets of signals here. The three protons in the methyl group are, on methyl groups, the protons are always identical. Okay, so here's a cyclic compound, a propane ring. And now I see one proton that's attached to the carbon next to chlorine. That's kind of distinctive. There's no other proton like that. But now I have these other two CH2 groups. And over here on this other side of the ring, I see that one of the protons is on the same face of the ring, the top face, as the chlorine atom. And it's always on the top face, the same face as the chlorine atom. The other proton down here is on the bottom face, away from the chlorine atom. Always. Nothing ever changes that. It can bend or flex a tiny bit, but that relationship is the same. So it's definitely clear neither of these is like A, and they're not like each other. So same face as chlorine, opposite face as chlorine. And then when I look over here on the other side, this proton on the top face, on the back side there, is definitely the same as B and has the same relationship. It's on the top face as chlorine, it's 2 carbons away from the chlorine, and I'd say the same for the bottom face. So here I see 3 sets of signals. I think because there's generally more protons and the protons are farther away from groups of interest, this whole idea of identifying inequivalent protons is a little bit harder with proton NMR. And that's just what you'll find. But it's the most important skill that you will have, is to be able to count up how many sets of distinguishable protons there will be in the proton NMR, just like it's very powerful in C13 NMR. Okay, let me give you a sense for why this will become more complex. And in theory, this is a problem that arises with C13. You just don't see it as often. Whereas this is going to give you fits. And it's going to bring you back to all that stereochemistry stuff that you had to deal with, I think, back in chapter 5 in the Gorzinski-Smith textbook. Okay, so we need to figure out whether protons are what we call diastereotopic or enantiotopic. This is a relationship. If 2 protons are diastereotopic, they will give different signals in the NMR. They'll have different chemical shifts. They'll do stuff to each other and cause some complexity. Protons that are called enantiotopic have a relationship of enantiotopicity will not be distinguishable in the NMR. They'll occur with exactly the same chemical shift. And we need to distinguish whenever we see 2 protons attached, especially attached to the same carbon, whether those are diastereotopic or enantiotopic. And I'll show you a way to do a stereochemical test to distinguish that. So let's take this example of butene. I could draw this like this, right? That's the simple line drawing structure. But here I've shown the 2 H's there on butene. And what I want to get at is, are these 2 protons going to be distinguishable by proton NMR? And the way you can reliably determine that is to use something called the z-test. It requires you to draw a lot of structures. Then here's the way the z-test works. What you do is you redraw the structure 2 times. Here it is. And here it is. And there's no shortcut. You can't just draw it 1 time. You have to draw it 2 times. And what we're going to do is, in one structure, we're going to replace one of the hydrogens with a fictitious element Z. I guess if you wanted, you could use iodine or uranium or zirconium, or just so we don't get confused, we'll put a fictitious element there that we could never confuse with a real proton. Now, on the other structure, I'm going to replace the other proton with an element, a fictitious element Z. So now I have 2 different molecules. And now all we need to do is establish the relationship between these 2 molecules. Are these 2 molecules enantiomers or diastereomers of each other? One way to do that is you could assign Kahn-Ingold-Prelog priorities. And in our little scheme here, you just assume that Z has the lowest priority, even lower than a proton. So if I were to assign Kahn-Ingold-Prelog priorities, I would do something like this. Priority 1, 2, 3, that would be the S configuration. And then I look over here and I see priority 1, 2, 3, but the Z is coming forward, so you reverse that. It has to be the R. These are enantiomers of each other. And what that means is, in this original compound, these protons are considered to be enantiotopic. That's the relation, enantiotopic. And so that's the relationship between these 2 protons. I would refer to those as being enantiotopic. And the z-test tells me that. And I know the z-test is a lot of work, but it's reliable. So, okay, so enantiotopic protons, those would give exactly the same chemical shift in the NMR spectrum. And that's important. Let's do another one down here. I've got a dichlorobutane molecule, and as I did before, I'm going to start off by drawing butane twice. And here I've got one chlorine going up, and I've got the other chlorine going down. I'm sure you know how to make that. And then I'm going to, this is a much more obscure example here. And I've got two protons, and I'm trying to decide, are those the same chemical shift or different chemical shift? Right? They're both next to chlorine, they're both one carbon away from a methyl group, but there's something weird going on here, and I can't tell whether I would expect the same chemical shift. Yeah, they're both attached to a carbon with chlorine, and they're both one away from a methyl group, but so what you do is you apply the z-test, you replace one proton, one of those two protons, with this fictitious element z. And then in the other structure, we replace the other proton with that fictitious element z. And then we try to establish the relationship here. So, in other words, what we would do is we would then apply the z-test. If you can't tell, if you can't flip it over in your mind and tell immediately whether those are mirror images or diastereomers, you could always fall back on assigning Kahn-Ingold Prelog priorities. I'm simply going to write what you would get here. You could do that on your own. It would just take you a little bit of time to do that. And because these are enantiomers of each other, these two, and I don't know if you can tell, but you might be able to just flip it around in your mind. And you'd be able to tell that that just like these two molecules up above, these two molecules up above were enantiomers, and that's why the protons are enantiotopic. These two molecules down here are also enantiomers of each other. You could build models if that's hard for you to see. And because of that, the relationship between these two protons is that they are enantiotopic. And that means they will have exactly the same chemical shift. They won't have a different chemical shift. So this is a lot of work, right? It's a lot of work to do this, but you will frequently have to distinguish between enantiotopic. And it's usually 99% of the time, this is caused by having a chiral center in your molecule, a stereogenic center. If you see a stereogenic center, you're usually going to have to be applying this test to try to figure things out. Let me take one more example here, because it's not always enantiotopic. There's sometimes cases where things are different. And here I see a chiral center in my molecule. It doesn't look meso. And so let's apply the z-test to this. What do I expect for these two protons? It's like here, one of them is kind of on the same face as chlorine, one of them is not on the same, but you could rotate about that bond. Is there some way to rotate it? So I start off by drawing my molecule twice. Okay, there's a bromine on the end, there's a chlorine on this carbon over here, and then I'll draw the molecule a second time. It's propane, there's a bromine on the end, and there's a chlorine on carbon 2. And now I'll draw my protons in. I'll draw this proton going in back here. There is no superimposable, so here's what I notice, is I notice that the stereochemistry of this center here is S, and it doesn't change between these two compounds. The chlorine is attached to an S stereogenic center in both cases by Kahn-Ingold Prelog. But if I look at this other stereocenter in my two molecules now, that's definitely the opposite stereochemistry in both of those. It's a stereogenic center in both of those. And so if I were to assign Kahn-Ingold Prelog here, it would be R stereochemistry in this case, and S stereochemistry here. Right, those are not mirror images. If it was truly a mirror image, every single R and S would have been inverted. Those are diastereomers of each other, these two molecules with this fictitious Z group in there. And because these are diastereomers of each other, that means the relationship between these two protons is that they are diastereotopic. And they're going to have different chemical shifts, different environments. And so you have to, whenever you see a chiral center in a molecule, you need to just get ready to, and you're trying to interpret the NMR, you need to just get ready to apply this Z-test to figure out whether those two, how many sets of signals you should see in the NMR. Whether pairs of methylene protons, H is attached to similar carbon atoms or the same carbon atom are enantiotopic or diastereotopic. Okay, so let's talk about chemical shift ranges for proton NMR. So here's a proton NMR spectrum, and I'm not sure why, but it looks like part of my spectrum is missing out here, so I'll try to continue this on. Spectra are usually plotted out to 10 parts per million. Every once in a while, you've got stuff down here past 10 parts per million, but that's unusual. So you'll find, so carbon NMR is plotted out to 200 parts per million, and proton NMR is typically plotted only out to 10 parts per million. So I can just look at the axis, and immediately I know whether I'm looking at a carbon NMR or a proton NMR. And there's other obvious differences as well. So what are the chemical shift ranges that you need to know to interpret these kinds of spectra? So down here, past 8 parts per million, this is where you see protons on carboxylic acids. Those typically will be shifted the most of any kind of proton. And they're, in addition to that, they're typically broad. The peaks aren't very sharp for those. Okay, down here from 8 parts per million down to about 11, but mixed anywhere in that range, you'll find H is attached to carbonyl groups, aldehydes, in other words. So they're all past 8 parts per million. As soon as I see a peak past 8 parts, and aldehydes aren't that common. So you won't see stuff down that far in the proton NMR. Oh, you know, somebody pointed out something that I made a mistake on in a previous slide, and I need to correct that while we're talking about this. So it had to do with me explaining to you this idea of downfield and upfield. So let me make sure I correct that before we go on. Well, I can't find it. So we call this region of the spectrum that's at high parts per million. Unfortunately, and this is totally counterintuitive, we call this the downfield area. So I would refer to all these protons over here as downfield. And then these protons at low parts per million, I would refer to those as upfield. But what I told you was that this is referred to as shielded, but that's not, that was the opposite. I had those reversed. This is what we refer to as deshielded. All of these protons occur downfield because they are deshielded. And over here, the things that are upfield because they are shielded. And I don't use the terms shielded and deshielded quite as often as downfield and upfield, but I had those deshielded and shielded reversed when I told you that before. Okay, so let's go back to this, to our chemical shift ranges. Here from 6.5 to 8.0, that's protons attached to benzene rings. Protons attached to benzene rings get shifted way downfield into this region. As soon as I see stuff in this region from 6.5 to 8 parts per million, I'm thinking benzene ring, and I start drawing plausible structures that have benzene rings on them. You might recall that there's usually a singlet at about 7.26 for your solvent, so don't count that as part of your benzene ring. So that's your chloroform contaminant from this deuterated solvent that we use. Okay, so from 4.5 to 6.5, those are protons attached to alkenes. So there's in C13 NMR, there's not a huge difference in the chemical shift ranges for carbons in benzene rings and carbons in simple double bonds, where it is so in carbon NMR, there's not a big difference between those carbons. But in proton NMR, there's a substantial difference in the chemical shifts for protons that are attached to either a benzene ring or a simple alkene. So at lower parts per million, that's where you see H is attached to simple alkenes. Now down here from 2.5 to 4.5 parts per million are the H's attached to carbons, and the carbons have some sort of electronegative atom on them. Oxygen most typically is the most typical one. Sometimes chlorine, that's not quite as typical in organic molecules, or bromine. Nitrogen, you won't see a lot of that stuff until chapter 25. Okay, so now instead of having an oxygen attached to that carbon, if you attach a pi bond, either a CC double bond or a carbonyl group, if you attach a pi bond to that carbon, the protons on there typically occur in this region 1.5 to 2.5 parts per million. So notice that this is not a proton that's directly attached to the CC double bond. That's over here. These are the protons that are one away. And then finally down here at 0.5 to 1.5 parts per million, that's just all the regular CHs. And usually this part of the spectrum is a mess for typical organic molecules because everything shows down there. Okay, so why do you see these groupings? Like, why do you see these chemical shift ranges? And I'm going to list for you the 3 types of effects that are causing these protons to appear in this region, or in these various regions. So what's the biggest effect that's causing these chemical shift ranges? Without question, the biggest effect is caused by the magnetic field of nearby pi electrons. So when I look down here, I'm going to ignore this carboxylic acid for the moment, but when I look down here, this H is so far downfield, so far at high parts per million, because it's directly attached to a pi system, a carbonyl pi system. It's a polar pi system. And benzene rings, they're way down here at high parts per million. They're directly attached to a benzene ring pi system. And then these alkenes over here, they're directly attached to a simple CC double bond pi system. So the things that cause protons to be shifted to high parts per million the most is being attached to some sort of a double bond. That's what causes the biggest shift. And being attached to an alkyne is not the same. I should say double bond electrons. It's being directly attached to an alkene type or a carbonyl type pi system. Okay, so that's the biggest effect. And then there's a small effect. And the smaller effects has to do with inductive effects. Inductive effects of electronegative atoms. So in other words, having electronegative atoms like oxygen or chlorine doesn't do as much. That only shifts you down here to the 2.5 to 4.5 parts per million range. I mean, it does shift you some to higher parts per million, but the effect is nowhere near as big as being on a carbon that's part of a CC double bond or a CO double bond. And then there's going to be tiny effects that shift protons. Tiny, tiny, teeny, tiny effects. And that is the magnetic fields caused by neighboring or nearby protons. And this is called splitting, and we'll get to that. So there's huge effects if you're attached to a carbon that's part of a double bond. There's small effects if you're attached to a carbon that has other heteroatoms attached to it. And then there's teeny tiny effects, and that's this splitting issue. Okay, so the effects are additive. So the more oxygens I could attach to a carbon atom, the more it will be shifted. So notice the aldehyde, it's shifted the farthest over here. Maybe not as far as a carboxylic acid, but not only is it attached to a carbon that's part of a double bond, but there's also one of those atoms in the double bond is an oxygen, which is electronegative. So that's why it's shifted farther than the benzene ring. And then the last is NHs and OHs, and these are awful. These are the worst, most awful things to have in a compound if you're interpreting the proton NMR, because they can appear all over the place. There is no special chemical shift range I can give you for these, for protons that are part of an alcohol or an NH, and I'm simply going to tell you that you can find them anywhere in the right, basically anywhere in most of this spectra. Right, OHs on carboxylic acids are past 12. OHs on alcohols can be out here at 5.5 or 3 or 2 or 1. And I promise you that's going to send you into fits, because you'll see this weird peak and you'll be wondering what it is. But one little trick I can give you is usually, but not always, those peaks are broader. They look broader than the other peaks. So they might look like this, whereas all the other peaks are sharp and well-defined. So one clue that can clue you into the fact that a peak in your NMR belongs to an OH is that often they'll be broad or broad end. Okay, so let's talk about these effects here, and I want to talk about this this effect of being attached to a carbon that's part of a pi system. So there's a device called a solenoid. It operates the car locks in your door. Anytime you take a wire, a coiled wire, and you run electricity through it, it creates a magnetic field right through that wire, right through the coil. So whenever you have electrons circulating around, it creates a magnetic field. And this pi system of a benzene ring, and it's hard to imagine the simple double bond, but it's also true for simple double bonds, is like a coiled wire. There's pi electrons here that when they get put into an NMR magnetic field, those electrons start to spin around. They start to circulate because of the huge magnetic field due to being in the carbon NMR magnet. And when they start circulating around, they create their own magnetic field. And that magnetic field that they create goes in the opposite direction of the NMR magnet. I guess on the inside of the benzene ring, they're going in the opposite direction. But on the outside of the benzene ring, that magnetic field is going in the same direction as the NMR magnet. So if you were a proton sitting on the inside of a benzene ring, there's no way to get a proton on the inside of a benzene ring, you'd feel a smaller magnetic field. But if you're a proton sitting on the outside edge of a benzene ring, directly attached to a benzene ring, you'll feel a bigger magnetic field. And that's what causes protons attached to benzene rings and alkenes to be shifted so far. So let's take an example of two different compounds here. Here's cyclohexene, no pi bonds on that. All the H's are the same on cyclohexene. And now I'll compare that to another six-membered ring, just plain benzene, and look at the huge difference. So cyclohexane, the protons are at 1.43 parts per million. Benzene, the protons are at 7.34. It's a huge chemical shift there. So these are shifted way downfield because they see a bigger magnetic field. The protons on the outside of a benzene ring. Now, some very clever people have designed super huge benzene rings. They're not benzene rings anymore, but where you can fit protons on the inside, and sure enough, those protons get shifted to lower parts per million. It's pretty amazing stuff. Okay, so typical benzene rings, way the heck shifted down to this kind of 6.5, past 6.5 parts per million. That's called magnetic anisotropy. Anisotropy means basically an uneven magnetic field that's created by those circulating pi electrons. Okay, so you don't have to be directly attached to a benzene ring to feel that kind of magnetic anisotropy effect. But the farther away you get from the pi system, the more diminished those effects are. So, so again, this magnetic anisotropy, those circulating electrons effect. So if I take a typical simple organic molecule like propane here, the chemical shifts for this middle carbon, that's 1.2 parts per million. And the methyl groups at the end show at 0.9 parts per million. And I'm not going to keep writing parts per million there. So that's for the protons on the two end methyl groups, which are the same. So that's a typical organic molecule, no double bonds in there. But when I have protons on molecules that have double bonds, it depends on how close the protons are to the double bonds. So the biggest effect I'm going to see is going to be the protons here that are attached to this carbon atom. And it turns out that those protons will appear at 5.3 parts per million. So I have a spectrum here of cyclohexene that has a double bond in it. And the protons that are shifted the farthest are the protons that are directly attached to the CC double bond. That's the protons here. Directly attached. They are directly attached to the carbons that are double bonded. If I look at these other protons, like here, these are not any longer directly attached to this. There's no CC double bond. This carbon here is not part of a CC double bond. If you're one carbon away from that CC double bond, the effect is greatly diminished. So now this is only 2.0 parts per million. You're still shifted more than just a regular CH3 group, but right, it's not like 5 parts per million. So now when we look over here, these two protons are showing only here at around 2 parts per million. And then when we get one carbon farther away, so now we're even farther away from this double bond. Now you're just seeing regular alkane. It's so far away from the pi system that it's really not feeling that magnetic anisotropy. And that's 1 part per million. And so that's these protons over here that are now, I guess, 2 carbons away. So these protons there, that's this this peak over here at about 1.7 for cyclohexene, as opposed to an ethyl group. Okay, so, and again, for a benzene ring, it matters how close you are. So here's a molecule xylene. It's a common solvent, actually, in organic chemistry that boils at a very high temperature. And so the protons that are shifted the most are the protons that are directly attached to the benzene ring. That's this proton here. So that's xylene. There's two methyl groups opposite sides of the benzene ring. So the protons that are attached directly to the benzene ring those get shifted the most, out to past 7 parts per million. But for the protons that are attached to the carbons that are attached to the benzene ring, they're 1 carbon away. They don't feel as much of that magnetic anisotropy, and so you can see that those protons are appearing here only at about 2.4, 2.5 parts per million. So that's the protons over there. That's those 3 protons in the methyl group. Okay, so it matters how close you are if you're going to feel this magnetic anisotropy. You have to be pretty close to the pi system. Okay, so let's talk about shielding and deshielding effects that are related to being attached to carbons that have electronegative atoms on them. So protons have an electron cloud surrounding them, and I've kind of depicted that here with this orange smudge business. And the intent is to try to depict how that electron cloud shields the proton from the magnetic field. If I were a proton and I've got my electron cloud around me, it's like I can't quite see the magnetic field. There's all this electron density there that's getting in my way. And so you don't feel the full magnetic field if you're a typical proton because of all that electron density around you. But electronegative atoms that are attached close by will help pull away some of that electron density. They will diminish that electron cloud. They will deshield you. In other words, take away some of that electron density, and we call that deshielding. So that's the effect of having electronegative atoms close by. So here I've drawn 3 compounds. This compound over here is chloromethane. That's the top spectrum. And the protons on chloromethane resonate at 3.05 parts per million. So a regular alkane would be down here at 1 part per million, but that chlorine atom shifts it way over to 3.05. That's the effect of that chlorine atom. But if I put 2 chlorine atoms on there, now there's an even bigger effect, that deshielding effect, where you diminish the electron density. The proton sees more of the magnetic field, and so now those 2 chlorines, now it's 5.3 parts per million. And we already mentioned this chloroform here, the chloroform solvent. This is the common contaminant in deuterochloroform. Now it's shifted to past 7 parts per million by having 3 chlorines on there. So this is shielding and deshielding. It is not as powerful of an effect as the anisotropy produced by nearby pi systems, but it's still a reasonable effect. So that can shift things. You know, it's not that often you're going to have 3 electronegative atoms on a carbon atom. That's a sort of extraordinary situation. Okay, so what else is powerful? This is let me show you this. One of the main reasons why proton NMR is powerful, and that is I can look at the area of the peaks, and I can tell how many protons corresponds to each of those peaks. And you can't do this with carbon NMR. That the area of the peaks tells me how many protons there are. So here's a compound with a molecular formula C8H10O. And I see 2 peaks in my NMR spectrum. 30 years ago, they would have had you'd rerun your spectrum and this little marker would go across your screen. And whenever it got to the peak, it would start moving up in correlation with the area under the peak. And so you'd have this little integration line here in red. And so what I can see here is my integration line for this first peak is only 1 centimeter high, and the integration line for the second peak is 1.5 centimeters high. So that tells me that there's 50% more protons under this peak. Now what I don't know from looking at that, what I don't know is why is that 50% larger? It could be this first peak is 2H, and the second peak is 3H. It could be that this first peak is 4H, and so you don't really know whether it's 2H versus 3H, right? That would lead to two peaks that have this kind of size difference in the integration line. It could be 4H and 6H, right? That would cause this second peak to be 50% higher than the first. You don't know. Well, the one advantage you have is you know the molecular formula. You can back out that it's not the 2H, 3H scenario because there's no other protons in the spectra, and your protons need to add up to the number of protons in the molecular formula. You also know that it is not one proton and 1.5 protons, right? There is no compound that has 1.5 protons. That's completely impossible. It's like all molecules have unit numbers of protons. So sometimes when you go to these spectroscopy websites, they'll give you these integration lines, and they'll just give you the heights of these integration lines in arbitrary units. It could be centimeters, it could be furlongs, it could be microns. I mean, it's totally arbitrary. But that's stupid, right? I'm not going to do that for you. In the lab, for the lab, they'll often give you peaks that tell you integration numbers listed below the peak, where it's like 2 or 3. And I'm not going to do that for you either. I'm simply going to tell you this peak is 4H or the peak is 6H. I'll write that next to the peaks. But I expect you to work the problems in the book that don't do that for you. And I'll expect you to work the problems on the spectroscopy sites that don't do that for you. Yes, question? I can't. No, I'm going to extend the sapling deadline probably to Monday night. Okay, so we'll finish up NMR on Monday.